more hierarchical, and reasoning at a different level than the. I didn't tell it, but if you have any question or clarification, you can just ask it directly, right? And of course, there will be a session at the end of this presentation. So let's try to take those observations into account and translate them into what could be a different architecture to do that. So moving away from the token representation, then we want to do some reasoning at a higher level. So in this work, we use what we call a concept. So I know this is like a very strong word, and it's maybe a bit overselling here, because for us, basically, at the end of the day, for us, a concept would be a sentence. Again, sentence is a strong word. Basically, it's like a sequence of text which is not too long, not too short, and eventually contains one idea. Okay, but this is not enforced in our case. Okay, so but here the goal is to have like a higher level, so a set of tokens that means one thing, whatever that is. It's not a strict definition. Okay, then so given this, we want to reason to do the reasoning on this higher level, higher abstract level. An idea for doing this is that the reasoning should not be dependent on the language you're speaking and the modality you are expressing the ideas. So we want like the concept to be language agnostic, modality agnostic, and so that basically we could apply to any input text or any input speech. Maybe that could make the understanding between humans better if we can really do this mapping between the realization of the concept, which are like the text or the speech that is pronounced in a particular language, and this high-level semantic that is expressed. We probably need some characteristic of this representation. So here we need like to compare them. So what we do is basically using an embedding space to represent those concepts. Okay, I will give you some details on this later on. And then eventually, like we said, to enable the hierarchical processing of information, then we need some multiple level of abstraction. So this is linked to the granularity. Okay, so token are needed at some point, right? We need them. Because if you want to generate text, you need to produce some tokens at the end of the day. But the reasoning could also imply some higher level, so sentence, concept. Why not even higher? Okay, we could process paragraphs or chapters, and then refine this and do the hierarchical processing. So this is like a continuum, okay, between the bytes. Some people could also say bit. Why not? Up to the chapters and the entire books, and try to do that. So all these are, been the motivation for designing these large concept models. So what is this? So the principle of the large concept model is to do all the reasoning in the embedding space, beyond the token level. So it's like I said, concept or sentence embedding space, which is based on Sonar. I will detail that just after. And basically, here is an example that if we want to do summarization, so we have the source text would be like the purple one, and then what we embed each concept or each sentences in the source document into this embedding space. So we have a set of vectors, each representing the one sentence. And what we want basically is to learn a transformation of this sequence of sentences into another one, which is the vectors representing the target summary. Okay? If we can do that in the embedding space, then the good thing is that we have modality for free if the space is multimodal or modality agnostic. And we have multilinguality or multilingualism for free, because since we are generating vectors, for those vectors we can decode them into any language that we would like, and then it's a big advantage. Another advantage that if we can like have a perfect embedding space. If you learn a task, this mapping task, if you learn it from, let's say, English data, which is abundant, then you could apply it to any language in the planet. So it's super efficient. But this comes with some constraints. You need to have an embedding space which is compatible across languages and modalities, of course. And then you have to learn this mapping here, which is like the tricky part. So here is the high-level architecture of the LCM. So obviously, we are processing text here mostly. So that's why all the explanations are based on text-to-text generation. So we start from words, or tokens, whatever. We have like an encoder, which will basically for each sentence or concept in the sequence of words, will generate one vector here. So this is done with Sonar. I will again detail this. So this is for us, this is the sequence of concept. And then, so this encoder here is fixed. It's so contrary to the JPA architecture that you might have heard of. Here we consider the concept encoder fixed. It's multilingual and multimodal. I will give you the details. And then the goal of this is to learn this large concept model here, which basically takes a sequence of sentence vectors and generate another sequence of sentence vector. And then when you're ready, like to provide the output to the user, then you instantiate basically. So you decode all those vectors into the desired language, desired modality. Okay, and then how to train these models. So we use diffusion process, but I will give you the details of what we tried and what we did in that regards. Okay, so again, the decoder is considered fixed here. So that's something that we may change in the future, but in this work we did that. Okay, so like I said, we need encoders and decoders. Okay, so this is based on the work, the previous work that has been developed at Meta, which is Sonar. So Sonar is a set of speech and text encoders and decoders. So how it is trained? So it's basically based like on a first model, which is a text-based. Here it's a multilingual text encoder. Which basically you have one encoder that is based on the No Language Left Behind 1 billion dense model. So this is a translation model, text-to-text translation model for 200 languages that we developed like 3 years ago. So here we take that can accept like 200 languages in the input. We generate basically a representation here, which is a bottleneck. That is obtained by attention pooling all the output of this encoder. So sorry, I didn't give any details here, but this is a bunch of transformers, right? We are all doing that at some point. Okay, so we have this Sonar vector here, which is a fixed size representation, typically 1024 dimension. And then we also train the decoder that can basically from this vector and only this vector with cross attention generate a target sequence. Okay, again, so how do we train this? We have multiple losses to train this. There is here the mean squared error between basically the representation of like translation to translation that should map to the same vector, right? Because for Sonar, it should be the same point in the embedding space. We also have the machine translation loss. So we have like 2 parallel sentences. We input one of them, and we want to generate the translation in the output. And we have 2 different auto-encoding losses. One is just the auto-encoding. So we try to reproduce in the output the source text. And the DAE, which is the denoising autoencoding, where we mask some tokens in the input and we try to reconstruct the full sentences. Okay, so this has been developed. There was like a lot of work in weighting those losses and trying to come up with the best result. I will give you some results afterwards. The advantage of this is that you can, based on this first model, you can actually extend it. It's very modular. So basically, if you want to add, let's say, speech encoders, then you use teacher-student learning, where you try to minimize the mean squared error between the speech input and the ASR, the transcription of the speech. You project them in the space and you try to minimize the representation. So in this way, you can really map speech and text in the same space, right? And if you want to, like, let's say you want to address a new language that is not included in the 200 languages of an LLB, then you can use the same methodology. The advantage of this is that you don't need a lot of data to train it. To train this student encoder here, even for your additional language. Yeah, you just use actually the knowledge of this big model to train the encoder for the new language. Another advantage is that when you train for a new language or new modality, you don't change the other one. Okay, so this one remains fixed. So the performances do not drop when you add another language, which is one of the main issues with current LLMs. When you have to include the new languages, you need generally to retrain it. You have, of course, adapters on many other methods. But globally, it's hard to cover more languages and without degrading the performances for English or the high-resource languages. Okay, so this is our base. So this was one thing that I didn't say is you can also create. We also created like one encoder for American sign language. Okay, so it was like an experiment doing this, but it was working quite well. So you have small videos of someone signing, and you project it in the embedding space, and you can actually do translation from sign language into any other language by doing so. So this have not been released, but all the text and the speech have been released. Okay, so a few performance results on Sonar. So we evaluate on two different tasks. One is the translation and auto encoding. Okay, so these are scores expressed in bleu. So a sentence piece bleu and comet. So here we can see that basically we lose a bit, of course, going through this bottleneck compared to the NLP model in translation from any language to English. So we can see that we lose a bit here, but again, the decoder, so the decoding is just based on one vector. Okay, so for some time ago, there was this discussion about can we really embed the semantic of a sentence into a single vector? And to some extent, it works. Okay, we can get quite a lot of stuff into this, given that this NLP model, has been trained for that purpose, for translation purpose, with and only that, with all what brings like a encoder decoder.
Dimension of this type of concept spaces.
So I should repeat the question. Sorry. Yeah. So the question is, what is the typical size of this embedding space? So it's 1K, so 1024 features. That's the typical size, yeah, that we're using. Yeah, and same thing from English to X. We see that we lose. So that is the consequence of using fixed size representation. Okay. But when we look at autoencoding, so really reproducing the target, we see that since NLP has not been trained for this, okay, it's really focused on translation, then the results are a bit lower for NLP compared to Sonar. Another kind of usage for this embedding space is the mining, okay, and the retrieval. So XM and XM++ are two variants of retrieval. So we have like a query sentence that we encode, and we want to find a translation in a bunch of text, right? And the difference between the two is that XM++ contains some hard negatives, where basically you just change one word, okay, one adjective, you change one adjective in the sentence. So it makes the task harder for the model to really find the closest. So the mining is done by really cosine similarity, a derivative of cosine similarity. It's a margin score, which is a bit different, but it's based on cosine. And here we can see that really the performances are really good. We can see that XM is much simpler. Okay, there is no hard negative. And here is the accuracy, the error. Sorry, the error. So we want this to be 0. Okay. Yeah, and these are the results when you process 98 languages, which is the intersecting languages. Yeah, so this is what we use as a start, you know, for in our architecture as encoder and decoders. We have Sonar and the representation. So the embedding space that we want to reason over is those vectors. Yeah, quick example of what you can get by auto encoding. Okay, you can see that here sometimes the sentences are quite long. In average, it was like 20 words in our experiments. And you can see that even given like a single vector, the model is able to reproduce mostly the sentence in its entirety, right? Since here it includes some translation task, and the model like change a bit of some words here that I highlighted in different colors, but it's pretty good. Okay, and it's been used. This kind of model has been used to mine data to generate some synthetic data to train the models, so NLLB models, and also the seamless speech-to-speech translation models. So we know that it works. In terms of speech, so when you train like a speech encoder, then you can do also some speech to text, zero shot. Okay, so basically the model there is no text decoder that has been trained especially. We just train the speech encoder with the teacher-student approach. And we compare this to the Whisper. So it's a supervised speech to text. So the Whisper has been trained for this. And you see that the results for different languages are quite good for Sonar. And it can like outperform Whisper mostly on languages that are probably Arabic is not really under-resourced. There's a lot of data for this. But Swahili here, it's the case. Gujarati, the same thing, right? So again, with a fixed site vector, we can do mining, we can do some translation, we can do some even speech processing here. Okay, so that looked like for us like a good start to achieve the LCM. Okay, so now I'm going back to the LCM, right? And here's a comparison of the features of each of the LCM compared to the LLM. So in terms of modularity, so here we can basically, if we solve the task, so if we train a model that can solve the task for one language, we have a zero-shot transfer to any other language and modality. Okay. In LLM words, you want to add one language, then you need to retrain or to fine-tune the models, and it's hard to fit all languages into those big monolithic models. Extensibility, that's what I was saying before. You can train a new one without interfering with the others. All encoders and decoders in Sonar are intercompatible because they are all trained to map to the same embedding space. Here in the LLM world, of course, you have modality and language competition. Okay, each time you want to add something, you need to eventually change the vocabulary and need to retrain, adapt the model. So it's a bit cumbersome. In terms of language coverage, so since it's based on NLB, we cover like 200 languages from the start. And for the LLMs, again, English, you have a lot of data, so we have very nice performance. But then it drops even for high resource languages, French, the performance tends to drop. Multimodal, yeah, but I already said it. In terms of efficiency, so since we are like compressing the input, so going from token to sentences, we basically which is much shorter sequences. Of course, it's been in the LLM. Is it really attending and looking at 1 million tokens currently? This we can adopt. Okay. And here, so it makes the processing more efficient. We use transformer with attention, and basically the attention is quadratic to the sequence length. Of course, there are some tricks to make it faster and tractable, but generally, like if you compress, you should be faster. I will show something later on. And yeah, I already talked about the sentence size here, right? Yeah, so this is like an overview of what the capabilities of the LCM based on Sonar. So compared to many different existing models, in terms of number of languages in the text modality, in the input, in the output, so we are based on NLLB. And then the different capability here. So we don't have any encoder decoder for the image, so we cannot process that, while some other models can do. And for video, so we had this American sign language. So this is really extensible. Okay, so this is the first attempt to the LCM. What we did is we went, straightforward way. Basically, what we did is that we have our vectors in the input. Okay, so sorry, the model we called it the MSc LCM. So we have like a sequence of vectors, and we want to predict the next sentence vector, right? So it's next sentence prediction in the embedding space. So here, of course, it's not like in the token world. We don't have like a vocabulary where we can do a cross entropy loss and use that. Here we need to generate a 1K dimension vector, okay, which represent the embedding of a sentence. So what we did is we did the most straightforward way. We used the mean squared error between the real next sentence vector and what is generated by a transformer decoder. So again, it's a very standard transformer with self-attention all over the place. We just like have a pre-net that basically adapts the inputs to the transformer, and then the post-net that basically generates the vector. Okay, you have some details here. The thing is, of course, this is not working well. Okay, so I have a question for you. It's not me who's working alone. Okay, so why is it the case? Okay, why anyone has an idea why this cannot really work?
There's no such thing as a sequence of concept, maybe the order ladder.
No, because we process some text, like a bunch of big text, and we have the sequence of sentences which come from text generated by humans, so should not be a problem. There was no.
He wants to input concepts.
Perhaps the code. Perhaps the encoder is not sufficient. Not really, no, because as I showed before, with Sonar, we can really embed multiple languages and a bunch of stuff. So I gave you like a small tip here.
Spelling error there. Maybe somehow concepts are not encoded cleanly when there is error in the input.
Maybe, but that's not the main issue here. The main issue is that basically, if you think about this first concept, once upon a time, okay, let's say it's a sentence. How many continuation of this sentence is plausible in English language? 1 million, right? A lot of them, right? So basically what MSE does, MSE tries to, from the same input, let's say you have once upon a time, you want to target each and every of those sentences here, which may mean completely different things. And MSE basically that will guide you toward the average of all the sentences, right? So you end up with one point, one data point, which is the average of all possible continuation of this sentence that are present in your training data, of course, okay? And given sufficient data, then yeah, this sentence, this average sentence, may not be suitable for continuation here. Okay, so if you think about like all the gradient and the training, you end up in the average. But it works to some extent. Okay, you can generate some vectors, you can decode them. Sometimes it's completely rubbish. Okay, sometimes it does approximate and give you a sentence which makes sense, but it cannot be like the way to go. And then, like I spoiled in the intro, so we went toward the diffusion process. So diffusion, have been heavily used in the image generation, where you want to generate an image based on a prompt. So you have like this an example here with DALL-E. So the quick recap on the denoising. The denoising is like two reverse processes. One basically which the noising process where you start from an image and you slightly add some Gaussian noise until you get you add some noise until you get a Gaussian distribution completely noised, and then you try to learn a model that will learn the process, the backward process. Okay, so basically, if you sample a noise from the Gaussian distribution, like here, then you want to learn to iteratively denoise the image and generate the original image. Of course, you want to condition that on some prompts to be able to generate this. You condition that on a text that explains what you want in the image. Okay, so this is like a very short overview of denoising. So our goal was say, okay, if it works for images, it might work or should work, I don't know, for sentence embedding. Why not? Okay, so what was the idea? So what we did is that we tried to consider two different architecture for the diffusion LCM. So the 1 tower and the 2 tower. So the 1 tower is equivalent more or less to the decoder only, in the LLM world, where basically we have a transformer. We have here the bunch of sentences here. So the clean one are in dark blue and the noisy one are in light blue. Okay. No, sorry, that's the reverse. Okay. The dark one are the noisy and the light blue are the clean ones. And basically, what you want is to generate the vector given the previous clean embeddings. Okay, and you do that with a transformer, and this is a diffusion process. So basically, you always try to predict your clean sentence vector, but you do that you have a diffusion loop that does this processing several times. So during training, of course, we need both noisy and clean, so that we can attend to the clean ones. Okay, otherwise we cannot really learn with a clean context. Okay, and during inference, of course, we have like the prompt that has been encoded here. Okay, here we have like the time step, so the diffusion time step. This is an hyperparameter that can range to like 1,000 time step or 100 time step. It depends on how many steps you want to perform your denoising. And then basically, so we encode so these are the denoised vector from the prompt, and we want, starting from a noise vector, which are time steps t, we want to generate the target, which is the clean vector, and we do that iteratively. Okay. So that's the 1 tower, and what we also did. Oops, sorry. Is it the one? Yeah, this is the 2 tower. So the 2 tower here, basically we try to separate the encoding of the clean context. So you have 1 tower, so 1 encoder with the clean context. So here would be the prompt, okay, where we encode them. And then we condition like the reasoner or the denoiser on with the cross attention on this encodings here. And we feed only one, basically one noise vector at the beginning, and we denoise it iteratively, but with cross attention to the context encoder, right? But apart from that, the main difference is that we separate the weights to encode the context and to denoise, while in the one tower, everything is done all together. For both models, the loss is the MSE, so we still have a MSE loss at the end. We try to predict the clean embedding, but it's done like in an iterative way by a diffusion process. So I skip the details for this. And for inference, it's the same thing, right? We don't in this setup, we don't change anything. Yep. One thing I didn't mention during training, since of course we don't want to attend to the previous, so the attention is a causal attention. We never looked, in the future. And also we used the classifier-free guidance. So classifier-free guidance, it's a method to basically train a model that can predict that can better approximate the distribution of your targets without having any context. Okay, so basically what we do is that for sentences, sometimes we completely skip the context. We don't look at the prompt and the previous sentences that have been generated, and we just generate without context. We just denoise the sentence. Okay, like this is shown to help in the image generation domain to generate images that look like real images instead of fake ones. Okay, and we're using it. We tried it for sentences. Here are some results on the pre-training. So the training stages are very similar to what is done for LLMs. So we have pre-training with unsupervised data, so a bunch of text basically, where we try to predict the next sentence, and then we have some fine-tuning with supervised data. So here we compare the three versions on different texts, so Wikipedia and the Gutenberg books, and we have a bunch of metrics here, which basically is like the L2 distance between the expected vectors and what we predicted, the round trip L2. So basically, after generating the vector, we can use the decoder to decode into text, okay, and re-encode this text into a vector and see whether basically what we generated, which is never perfect, can be decoded by a decoder and make sense basically. So that's the round trip. We have the paraphrasing here. So it's whether we paraphrase the text that is in the prompt. Okay. We have this contrastive accuracy here, basically, which try to evaluate whether what you generate is closer to what you have than you target than any other targets that has been generated. It's something that basically shows that the model is not generating completely unrelated sentences. Okay, and the mutual information between what is generated and what we can see is that, as I said before, the Basel CM, MSE transformer with MSE can still decode some sentences that somehow make sense sometimes. We see all in all that the L2 descent is actually quite close, which basically, contrary to what I said before here, means that the model is able to generate some vectors that are close to what is expected. Okay, but this does not mean necessarily that when you use them and generate a text output, then you generate the real sentences. Yeah.
So if your model is learning concepts,
yes,
one would imagine that those concepts are somehow reusable in other settings or are somehow in this concept space because they spread over different things and represent in different languages, different things, etc. Or that is your claim.
Yes.
So
This is a very good point. Actually, this sentence space is really sparse. Yes. And in the paper, so I'm not showing it today. Sorry, I didn't repeat the question, but yeah, the goal is, I think what you said is that the space is reusable concept and it's a sparse space. And this is very this is true. There is an analysis in the paper about what we call the fragility. And basically, we try to evaluate, how sparse is the space, and if you miss, basically, you target by a small distance. Do you end up with a correct sentence in the end or not? Okay, so I think that's related to your question, if I understood well. Huh?
About this, you directly go to this 1,000 dimensions.
Yes.
Rather than somehow building from some protection.
Okay, so
like this,
yeah, so the question is, we are going directly to the, we generate directly the 1,000 dimension vector instead of going through some intermediate step, maybe with smaller sizes first. So actually, the diffusion process, yeah, this is true. We generate directly the vector, but we do that in iterative steps, right? The diffusion process does the denoising step by step. It's not like we are projecting, so we can expanding the vectors and like compressing it. No, we are really just denoising the vector. So in our setup, I'm not sure how we should like generate like a smaller vector that would be like a more compressed vector and then or generating a larger vector. Yeah, I'm not sure how we would do that, but yeah. Okay, so here basically what we see is so the base ACM tends to generate closer vectors than the other models, but in the end, when you look at the mutual information, for example, or the contrastive accuracy, you see that the content of these vectors are less related to the expected output, right? And we see that basically for both data sets here. Conclusion. So this should be taken with a pinch of salt, I would say, because it's really hard to find like metrics in the embedding space that really make sense and that are really meaningful to evaluate the pre-trained modeling. Okay. Then for the model that we train, maybe I should go faster. We are basically focusing on some tasks. So in the LLM world, you probably heard about this MMLU, GSM8K, GPQA. So these are like MCQ style, so multiple choice question data sets, where basically you have like 4 or 5 choices and you need to generate the letter corresponding to the correct answer. Okay. We have like, so one thing is, it doesn't really show, whether the model is really reasoning and doing intelligent things. Okay, it's not representative of human intelligence. That's one of things that we argue with. And also, since we are working at sentence level, I must admit that it makes our task much harder when you have to really find some token level information into an embedding compared to having the tokens directly. Okay, so we address this task still in the paper, but what we focus really on is the generation tasks. Okay, where basically, for example, we consider the abstractive summarization. Okay, when we try to generate a summarization without just selecting sentences from the input. Okay, so we have like a different corpus. We created one corpus that has been open sourced, the LCFO, for long context and long form output. So the idea is going toward hierarchical decoding, right? So that's why we tried this. And also we sort of did this reverse summarization, which is a summary expansion. Okay, given a summary, can you recreate the source document? Try to generate more than one you have in the input. Again, that should be quite interesting to do if you reason at a higher level. So here are some results. So Rougel to evaluate the n-gram matching with the reference, and a coherence metric given by another model that has been trained on completely different data. So we compare our models to what we call the small llama. So it's a small LLM that has been trained on the same data as the training data used for the LCMs. It's a small large model, exactly. Okay, of course, the goal was to really compare with a model that has been trained on the same setup. And of course, it's probably a disadvantage for the token base, but you will see that they still perform quite well, even with less data. So here, for example, you have like the Rugel for summarization, okay, where we really see here the difference between the base and 1 and 2 tower. So both variants here end up with very similar results, okay? And we can see here that even the small llama, so this was like, if I remember, so the llama with equivalent size, which is 1 or 3B, I don't remember. And they outperform a bit, you know, the LCM here. Yeah, so I was telling you about that earlier. So in terms of efficiency, this is the theoretical efficiency of the LCM. Okay, so basically here I have the number, the context size in tokens. Okay, and you see the number of floating point operation for the LLM reasoning at token level, and what an LCM would provide given different sizes of the LCM. There is still something to take into account. So of course, here we do the reasoning at sentence level, but we have the encoding and the decoding parts if we want to have tokens in the input and the output. The advantage of this is that you could encode, you can do that in parallel, okay? You just have a small overhead, but you can do the reasoning for the previous sentences and encode in parallel, basically. So an LLM cannot do that. Then, so these were for like the 1B and 3B, so 3 billion parameter model. And then we scale it to 7 billion parameters. I'm not going to describe all the metrics here, but we have like different models, and we compare to models that have been published as open source. Okay, again on the summarization task. Okay, XM, and we see that we obtain Rugel that are better than the token level. So here, XM, I forgot to mention this. This is multilingual translation, right? It's not just English. So in average, we perform better than the LLMs here. Again, I don't have the time to describe this. And on the summary expansion, so that's something which is interesting. So going from a summary and try to regenerate the document. An interesting thing is about the variance ratio. Basically, this means that this is the proportion of the extension. So given a source length of 1, Gemma, for example, will extend it to 6.8 times. Okay, so we can see that the models are doing quite similarly. Llama generating like longer documents. This end up actually having a better Rugel, which is Rugel includes the recall. So okay, there's a precision. It's a F measure, so you have the precision, but the recall is really helping here. And for the I think the factor was 7, you know, between the summaries and the input and the text. Or 6, sorry. Yeah. Okay, so we are like generating something which looks like the real size of the size of the real document. Okay. And then, yeah, okay, I don't have time to describe this, and I'm going to follow up. Okay, and then we did on the Excel sum, so with 45 languages. It's abstractive new summarization, and we compare to the insert fine-tuned Llama in 8 billion parameters that officially support 8 languages, but it's been trained on much more. It's officially support them because it's been like guided and some guardrails in order to not generate inappropriate content. These arrays have been trained for 8 languages. Okay, and then we compare that to the LCM. The LCM has been trained with English data only, so it's really zero-shot transfer for the 44 non-English languages. Okay. The results. Basically, we can see that we can perform a llama model trained on multiple languages. Okay, so we have like a few, I would say, losses. Japanese, which is really present in the data. Here, this Chinese, Gaelic, but in any of languages, okay, we can have big wins, especially for the languages that are low resourced. Okay, Burmese, Sinhala, Tamil, etc. Telugu. Okay, a bunch of languages where we can really improve a lot. This is here the coder initialized with an LLB does help here. And again, it's zero-shot transfer against llama models trained on a lot of data. Okay. And yeah, then we started to do the first step to the hierarchy. The also content. So here, basically, we try to generate the content on the page presentation. Basically, it's a vector that represents full paragraph. Okay, and again, here we try to condition. We are not generating any page vector. We are just generating sentences, but condition on this. Okay, and it was very preliminary work, and we show that we have like not impressive, not really impressive results. But again, it's a step towards more hierarchical processing and reasoning and doing tasks at different levels. And I'm almost done. So here, what I presented today was like our to do modeling at a high-dimensional embedding space. Okay, over those concepts, which are like sentences. And again, sentences not too long, not too small, encoded with Sona, which is multilingual, multimodal. And probably one of the first application of diffusion, large-scale application of diffusion for NLP that we have looked. Again, we explored several architecture. We show very strong generalization across languages and modalities. It's not like the LLMs across the board and reaching, the result that we were expecting. But still, for first attempt, I think it shows like some very good capabilities. So as a conclusion here, I would say that there's still a long way to go. We are still working on this. Next sentence prediction, predicting continuous vector is really, really tough. The that I showed you, it's much different from token vocabulary of a few 100K tokens. We don't have access to a softmax that could provide some probabilities, so it's hard to have to know whether the generated sentence is actually a good sentence. Okay, so you need to involve the decoder and to do something else. The embedding space design. So the way we did was working with an embedding space that is fixed, encoders and decoders were fixed. Probably at some point we will need to release that constraint. And it's very important to have a space that is robust, to divide. I think one of you talked about when you have a wrong input and slam changes. So this embedding space should be robust to this. And so we presented some diffusion model that maps the Gaussian noise to this embedding space in order to generate the next sentences. Yes, that's a new paradigm. It's still ongoing. Yeah, we like it because multilinguality and multimodality for free is like very appealing. So hopefully we'll make it work even better in the future. Thank you very much. So the paper is available on arXiv. It's attracted a lot of attention of the community, not necessarily all the scientific community. Some papers have been, showing some work with this. And yeah, have a look if you like. Thank you very much. If you have any question? Yes, please.
I have two questions. So the first explain which the LLMs are doing one element at a time. But also at the same time, it's regular, also inside they have a very same architecture similar that you have. Because basically, when you say something, it's just a sequence of sentences debate, right? And the longer you say the sentence, probably the word will work because they will have more information to compress into a single vector. But the regular LLM is doing this also. Pulling all the other tokens, potentially representation of any sentence regularity. When we're saying what to predict next word, please by attention. Power task that was so here where the tokens is really important.
Yes.
And then the notion of concept. How do we define it? It's just a sentence equal or there are words that alone words that are not concept. So it's hard
to repeat this question, Mark. Okay. So
you may only get close.
Okay.
You may. Oh no, it's okay. Never mind.
Yeah, it's here. A token, the tokens do information and then the question is that our method is actually doing this with a fixed segmentation, so fixed sigmoid. You said, I think, to perform this pooling. That's one thing. And then it's not robust to the length of the sequence. I think you mentioned this. Yes, so that's true. And so the final question was, I missed it. Is yeah, the token, there is the token information times for some task is and here evaluated with. So yeah, so you are right, and for the multiple choice question, we have to basically to select the letter that correspond to the correct sentence. We struggle, I mean, LLM struggle to do that. And token level information is harder to add the information. It can recreate some amounts of tokening in this sentence. I mean, regarding the what LLM do, you're right. The LLM does this kind of reasoning at a high level. It's been proven, I think, at that layers. The problem is that nothing is explicit. Nobody understands now currently what is going on, where in the information, what this particular here and there. But as of today, nobody can tell. Okay, this LLM works like this, and the reasoning is done like that, right? And this work is an attempt to have explicit modeling. I agree. Our definition of concept is fuzzy. Okay, it's nothing to compare to the linguistic definition. I don't even think actually that there is a single definition of concept. I agree. One word can be a concept. 2 words. It's not deterministic. Here was really the focus was to let's try to reason a level with some chunks that are mostly containing a single idea, whatever it means. Regarding you're totally right. If you embed in one vector, the longer the source sequence, the lower the performances into auto-encoding, in translation, anything. Yeah. The text and segmentation in this approach. Or we need to remove this constraint to consider more flexible segmentation, but it's not done with the attention weight we are doing self-attention. It's done beforehand with some other models that tells us what is a space. Okay? So yeah, you are right. And did I answer your question? So basically, the goal here is an explicit modeling of what is a concept, while in the LLMs it's done in an unsupervised way. And the thing is also we don't really know how this happened and what is going on in the internals of the LLMs. And here we wanted to really provide some information. Given that we are using transformer too, so we are mixing information too, right?
They're actually somehow getting access to
Okay, so the question is it better to have like one sequence of embeddings compared to sequence of text tokens? I think, to be honest, I think we will need both. For me, the hierarchical and the multi-granularity, the multi-resolution, it's like multi-resolution analysis of signal, where you have maybe at the beginning you have, and then you have sentences, you have a paragraph, and probably the big answer of this will be a model that can switch from the granularity when it's needed. Because for some question, you're right, you have a specific token. For many of the tasks, and it's better to reason at high level and just dive and zoom in when we need.
Certain references or certain, or even I think that this model could potentially also struggle to have coherence. Let's say, because since you have a sequence of no longer a sequence of tokens, you have a sequence of
sentences,
some point when you need some coherence with specific, also like the same name of the character, let's say.
It's in the vectors. It's there. The information is there. Now, how we make the model able to really catch it through the cross-attention? I think you would be surprised how much information about name entities and are in the sonar vectors. It's not that bad in that regard. Yeah. We can continue maybe after. Yeah.
Question. Is there an ablative study where you sort of increase the dimension and figured out what is the optimal dimension? That's question 1. And question 2 is, did you sort of look at, in 20 years ago, people were doing all these ontologies for various concepts in various things. You see perhaps clustering around some of these ontological things.
So first question is about increasing or changing the size of the embeddings. And second question is whether the concepts that are trained can be matched to like ontologies that have been created. For this work has been done in the work to increase. We didn't revisit it, and the sound decoders are available that have been published. And no, we didn't try. What we saw that we did the first work on the page model, so paragraph vector. Here you need more capacity. Yeah, need more features basically. At 1K is not enough basically. So that's for the first question. For the second question, so we haven't even mapped this to the ontologies. Again, our usage of concept here is really to move away from the token. It has nothing to do with all the linguistic analysis and trying of modeling of what is a concept really. For us, it's really a sequence of text, okay, which is not too long, not too short. Even if we don't fully control that in our experiments, with 1 or 2 tokens, basically, it can happen. And the goal is really to model this chunk of sentences, right? But large chunk model was less appealing than large concept model. So that's why we use concept. Yannick, sorry. I passed. Where is it? Yeah. I passed really. So no, we haven't tried to properly evaluate the speech. Oh, sorry. So the question was, have we tried to use the speech ASR or speech whatever task based on speech? So no, we haven't tried it. But it could be done. I mean, Sonar comes with like almost 80 encoders, I think, for speech. And no, we haven't tried this. But we did what we did basically for this is so no generation, so no LCM, but those work when you have a speech and want the ASR or the translation, it does work. So we would think it would work the same way as the zero-shot generalization over the languages. But this has to be proven. Yeah, we haven't done it. Yannick?
My question is about flexible segmentation. You mentioned this flexible.
Yes.
Really, if you want to process speech, for instance, or speech to analyzation, notion of the sentence is not so clear because it's very soft when you want to the right thing and not really. And so I would like to know if you know any place with this kind of people who work mainly on the text. So I don't know if you try to send some data, for instance, by something else that the point again.
Yeah. Speech, for example, the segmentation is fuzzy. It's not a strict. There's no strict definition for what a good. And the question is, do we to do that? Right? So. Yeah. Yeah. Well, yeah. Exactly. So we did some analysis but more on the Sonar side, not on the LCM side. Basically, if you have a text, you do different segmentation, and what kind of vector do you obtain, and above all, how do you reconstruct it and get like good reconstruction or less. So this is more on the Sonar side, and segmentation is super important. Yes, of course, right? And that's an issue. That's why I think at the end of the day we will need all the levels. Right, we need a more at token and choose the level at some point. But to answer your question, Sonar has been trained with what we call the over segmentation. So basically, we take a text, we do different kind of segmentation. We grew, so we perform sentence segmentation. Nothing to do with like a sentence ends with start with a capital letter, ends with a full stop. No, it's really segmentation in chunks. More, again, the idea is that one chunk should have one idea, right? So one thing. So we have multiple chunks in a sentence, I would say, and we try to merge some segments and to have different so that it's robust to the input here. For the LCM, we didn't have the time to consider really, the different segmentation and see the impact. No, we did just like on the sonar side, reconstruction and stuff like this. Yeah. But yeah, that's a big issue. But to Demos.
So Demos is asking, the model assumes that tokens belonging to different sentences are conditionally independent given the concept vectors of these sentences. Have you observed any sign of unnatural contextualization on inconsistencies between the sentences?
Okay, so the tokens in different sentences are considered independent. So because I guess the question is about each vector is encoded separately. So
consistency between the sentences. If there is actually some kind of unnatural contextualization, like
no, again, it's I think it's what we observe is that segmentation is important. So yeah, if you segment badly, then you miss some information to properly encode, then you will end up with something which is not perfect. But did we observe any weird stuff? Not particularly. No, we haven't looked at that precisely. But yeah.
And then Fatih was asking did you check if the concepts are learned better for some languages?
Oh yeah, but again, this is on the sonar side. Yeah. Of course. The sonar does not perform equally, across all languages, and again, the low resource languages are generally less well modeled. But again, I think it's still usable, and you can as exemplified by the result that we have on the zero-shot summarization, even for languages where we don't have like a lot of data. And again, here the model has been trained on English only, and yeah, I guess here if the segments were not meaningful, even for other languages, I guess we would not obtain as good as results. So I think I can So there was there first and then there. Yeah. Yes.
So kind of a similar thing, except it's it focuses on different aspects like scaling and stuff. But I train this architecture end to end. I would ask, apart from kind of the structural nature of using sonar embeddings as kind of token representations, is there any other reason why using diffusion might be more advantageous compared to perhaps train such architecture end to end generating?
Sorry, I didn't catch the most important, but the last part. The question is,
what kind of compared to trying to train this architecture end to end, maybe for generating the final tokens, kind of like Python.
Okay. So the question is, so there is this byte latent transformer BLT model which operates at byte level and do some patches to combine the bytes and generate the target. And we are using sonar, so sentence level. And so the question is there an advantage in using sonar compared to using training an end-to-end version more similar to BLT? Is that the diffusion part? Okay. So I think for me, the diffusion part is really to address the issue. If you if just do a women messy, then since we it's hard really to basically you predict the age of the sentences, with and the diffusion process will basically depend the prompt where you start will follow a path and end up with one of the possible translation instead of ending up in the so that's the motivation for the diffusion. More that way, we would be happy to use it. Regarding the differences between BLT and what we did, and training end-to-end compared to what we're doing. So training end-to-end is also like the embeddings predictive architecture that is pushing for, not the JPA architectures. The problem is it's really hard to train all this, all together. It's to have like meaningful representation that could really be useful. And again, we want an explicit reasoning with explicit chunks. Okay, that's what we did here. We know that that's somehow one idea in our sentences, and so training end-to-end is difficult, and especially for text. Regarding like the operating at byte or sentences. Again, so what they use in BLT is an entropy-based method to do the patches. We could apply this here. We opted for like an ad hoc segmentation method, but that's definitely something that we could use, as an alternative. Would it change the results? Maybe segmentation is important. Would it be better? But I'm not sure. There was a question here, I think, right? Yeah.
There is people the embeddings for the sentence embeddings could be replaced. So what are your thoughts on like this using a very old approach like skip sorts, which are trained using the context sentence, right?
Yeah. So the question is, the embedding we're using could be replaced by skip sort, which basically was a recurrent neural network, I think, to predict the next sentence, the token of the next sentence. Or the previous sentence, yeah. So using another embedding space, we have considered it, and we tried over available embeddings. We haven't published on this because we didn't do an extensive study on this. And yeah, definitely. Sonar is not perfect. The version we use basically has been trained mostly translation tasks, and probably we need to train it with, like I said, the next translation, different tasks, even some supervised tasks. Why not? Just to train the representation, and so that the representation already contains something about what you want to do with them. So that's something that can definitely be improved with regard to what we've done here. And skip sort or LabC or any other can be considered. Yes, definitely. Again, which one would perform better? I cannot tell you. You need to try first. So yeah. Sanjeev or there?
Correct. So the diffusion here is just to say, instead of having the next sentence embedding based completely and purely on the previous sentence embeddings, because as I said, if I have always the same prefix of sequence of embeddings, and I have multiple options, at the end the model will just learn the central.
With MSE, yes.
So basically, the trick is saying, okay, I will have the same thing, but not only based on the previous one, but some random. So the model will always have the noise as a seed, kind of, based on this random noise, it goes as a seed, kind of to get the prediction of the next one. And this way we can disentangle the prediction of the next sentence from purely the previous ones. So it's like that, more or less the trick.
Yeah. So the diffusion. So the question is, explaining the diffusion process and why we chose diffusion. Do I understand correctly? Yeah. Yeah. Yes. It's not because the diffusion process is an iterative process. Okay, so you don't generate directly the vector, the continuous vector. You do it like by refining and denoising, iteratively the vector to reach one of the possible target. This where you land. and we continue with the text. So the pre are cautioning the noise. And yeah, the motivation for that, is exactly what I was saying before. Is because if you do MSc, you end up in the average. Alternatives is very easier alternative. For not in general, but so basically to modeling the target distribution rather than just predicting the next so there is the VAE, so variational autoencoding that can help having some latents also, but it generally I think one of our colleagues tried this, but just to consider to determine whether we should go, and we couldn't really make it work. So and there is let's say the how's it called, the new generation of diffusion, which is I missed the name now. I'll find it again. Sorry, there's another way which is supposed to be more efficient, but it's in the diffusion world, I would say. But no, I don't know any easier way of doing this for now. If you have ideas, I'm happy to discuss. Sanjeev, you had a okay.
So just add a quick comment, when we said in the beginning, maybe you're exaggerating by calling it a concept modalizing, you're exaggerating.
Yes.
Because, if you said this model is able to do things like similes or metaphors or idioms or something, that's
not at all
really beyond words into concepts. But that's not the evaluation. You had a bunch of evaluations. What I'm wondering is, if you really had a good sentence representation, wouldn't it be useful in compressing the context? So instead of having a 1,000, like, a 10,000, 20,000 word context, have 1,000 sentence context. In other words, use it to represent the context of the model, so that all the information that's there in the actual words, you can compress them to individual sentences. So is there some evaluation like that you could do, or are you thinking of doing?
So the question is, so we are using sentences. So in the context, we are compressing the context into sentences, right? And
yes, perform some task using these as the context embeddings.
But that's what we're doing when you do summarization. Even when we do a multiple choice question, the prompt, it's segmented into sentences, and we transform it into vectors, and then we try to predict basically the sentence vector which contains just the letter corresponding to the answer. That's the way we would process an MCQ. That's why the task is harder, as regarding the discussion we had before. Yes, for us, we don't have access to the tokens per se, so it's a bit harder for us. But the task, every task that we do, we don't have tokens in the context. No tokens. It's just sentence vectors, right? And then we try to predict the sentence vector of the answer, basically.
The sentence vector of the answer, just actually perform the task.
So predict tokens, right?
Yeah.
But that's something. But it's
runtime cost.
Yes.
Not requiring.
Exactly. I think this is exactly one of the goals, and that's why I think at some point we'll need to have like the multi-resolution. So have the tokens, maybe the closest context could be like in tokens. So that if you want to answer one question with, it's hardly the case that the answer is like I don't know, 1,000 or 2,000 tokens away. It's, I think it's probably you have a lot of information in the short context, so we could keep that as tokens and maybe compress, the history, the longer history with vectors, and try to mix that. The problem is that, you're different granularities. It might be tough for the model, but that's the idea. Compressing the history is one of the advantages of this approach. but it makes things harder when you need to have a particular token and to get there. It's there, the information is there, it's much harder to fetch it. So the last one?
Might be a little connected, the performance evaluation that you showed, it was just the LCM part, right? There was no data for encoder or the decoder itself.
So yeah, encoder decoder were frozen. So basically for this kind of task, so the model were pre-trained on unsupervised data. Speed. Yeah. Yes. For this is a theoretical speed without the encoders and decoders. The advantage with our method is that you can encode and decode in parallel. You know?
Some of the computational power needed for running, is it more efficient or?
Yes, it is. Basically, one sentence in our experience is 20 tokens. Okay, so even if you need to encode it, then when you do basically you split like an LLM is doing token to tokens, very long sequences with the attention. So of course you have some tricks like local attention. You have the KV caching and all these tricks to make it faster, but still the computation and the number of flops, if you do full attention, is quadratic, right? In our case, we compress like sequences by a factor of 20 in average, right? So it's and then we use the same components. It's transformers. So yeah, there is this gain in the middle, and then we have this overhead of encoding and decoding. It's the flops that have been calculated given the architecture that we tried. Yeah.
I have to cut it. Thank you very much, Loïc. Thank you, everyone. For the technical problems and just announcement for this Friday, we have planned FLab Redance talk again for 11 a.m. hopefully with working minds. Okay, thank you.
Thank you.
March 30.
That's good.